everybody. Today's lesson is going to be about simplifying rational expressions. But before we get into simplifying, we need to talk about rational functions and what they are. So here's a quick definition for you. A rational function is a quotient of polynomial functions, which basically just means it's going to be a fraction of two polynomials. So for a couple of examples, here we have x plus 3 over x minus 5, which is a linear polynomial over another linear polynomial. Looks like a fraction. Here, our second one is 1 over x plus 1, which is a constant, which definitely counts as a polynomial, over a linear polynomial x plus 1. And number 3, we have a linear polynomial x minus 5 over a quadratic polynomial x squared plus 10x plus 16. So these are what rational functions will usually look like. And now we can move on to see some other attributes of rational functions. Now let's explore some interesting attributes of rational functions. And in fact, we're going to use 1 over x, which is the parent function for rational functions, to discover something really important to know about rational functions. So to take a look at the graph of f of x equals 1 over x, we're going to use the table to help us make a graph. So I'll start by plugging in x equals 1. And the function 1 over x means I take 1 divided by whatever x value I have as my input. So 1 divided by 1 is equal to 1. So I get about 1, 1, which I'll place about right here. Now I can try with x equals 2. Now in this case, 1 divided by 2 is going to give me 1/2. So when x equals 2, my y value is 1/2. It's a little bit lower. If I try to go a little bit further, let's try x equals 4. What my f of x value, my y value, is going to be 1/4. So I go even further and it gets even closer and closer to the x-axis. As you guys can see, if I increase my value of x, my value of y decreases. I can kind of do the same thing if I decrease my value of x. Let's say I use x is equal to 1/2. Well, 1 divided by 1/2 is the reciprocal of 1/2, which is equal to 2. So when x is equal to 1/2, my y value will be equal to 2. If I use x equals to 1/4, well, I get a value of 4, the reciprocal for my y. So I get even further up to closer and closer to the y-axis. Now, as we push together all of these different x and y values, you guys can see that it forms this type of graph. We call this a hyperbola. Now, we're almost complete with it. Of course, we also want to look at negative values. But all the negative values are going to do, if I plug in, for example, -1 for my x value, it's just going to give me a -1 for my y value. Same thing is going to happen whether I plug in -2, it'll give me -1/2. -4 will give you -1/4. And so on. And so we will get another branch of the hyperbola that looks like this. Now, the one value we haven't used yet is a very, very important one. And that is x equals 0. So when x equals 0, well, according to the function, we would do 1 divided by 0. But that is a problem. This is undefined. And an undefined value can't be used as a part of the function's domain. So we usually state that f of x is equal to 1 over x for all values of x except x cannot equal to the value of 0, because it'll give us an undefined value. So, because certain values of x will result in undefined values for our rational functions, we have what are called excluded values that we must consider when you're dealing with rational functions. Excluded values of the domain are those x values that result in the denominator being equal to 0, which would of course give you an undefined value. So let's take a couple of examples really quickly to show you what I mean. In our first example, I have 1 over x plus 2. So normally the domain of a function would be all real numbers. However, we're dividing by a polynomial x plus 2, which might equal to 0, depending on which x value we choose. So to make sure we don't get an undefined value, what we do is we take our denominator, x plus 2, and since we don't want it to equal to 0, what we do is we say it's not equal to 0. So we set it not equal to 0, and then we solve for x. In this case, we subtract 2 from both sides, so we solve that x cannot be equal to negative 2. So that value is excluded from the domain of our function 1 over x plus 2. In our second function, here we have x plus 7 over x plus 3 times x minus 5. Well, here we have a factored quadratic in our denominator, so that means we can use the zero product property, which will let us know that either x plus 3 cannot be equal to 0, or x minus 5 cannot be equal to 0. If either one of these two factors equals 0, we have an undefined value. Once again, solving for x for both equations gives us the fact that x cannot be equal to negative 3, and x cannot be equal to positive 5 in our function. Now, before we can discuss simplifying rational expressions, we should start by simplifying fractions, because this will show us the way that we can simplify rational expressions. So let's start with this first fraction, example 1, 3/9. So the basic idea of simplifying a fraction is that you can cancel out factors that both the numerator and the denominator have in common. So it's useful to factor both your numerator and your denominator as much as possible. So, for example, my numerator 3, well, factors of 3, it is a prime number, so only the numbers 1 times 3 are factorable this way. 9, however, can be factored to 3 times 3. So, as you guys can tell, I have a factor of 3 in my numerator and a factor of 3 in my denominator. Since 3 divided by 3 is equal to 1, we consider these two 3's to cancel out, leaving us with a simplified fraction of 1/3. Similarly, with 20 divided by 8, we can find common factors of 4 for both 20 and 8, 20 being 4 times 5, and 8 being 4 times 2. Since I have a 4 in my numerator and 4 in the denominator, they divide equaling 1, which means they basically cancel out, giving me a simplified fraction of 5/2. Simplifying a rational expression is pretty much the exact same concept as simplifying a fraction. What you're trying to do is simplify and cancel out any common factors between the numerator and the denominator. Let's take a look at a couple of examples. In our first example, I have 15x cubed divided by 3x. To simplify this fraction, we can think of 15 as being 3 times 5, and x cubed can be thought of as x times x squared. 3x, of course, can be thought of as 3 times x. So we have common factors that can be eliminated from our numerator and denominator, 3 and x, leaving us with 5x squared divided by 1, or just 5x squared, as our simplified rational expression. In our second example, as you guys can see here, we have x plus 1 divided by x plus 1 over x minus 5. We have a common factor of x plus 1 in the numerator and the denominator, so they can be divided. In our numerator, even though it seems like our only factor has been canceled out, remember that 1 times that is always a part of any polynomial. So we're left with 1 in our numerator, and only x minus 5 remains in our denominator. A common misconception that you have to watch out for, that students make mistakes on every year, is to only cancel out common factors, not common terms. Let me give you a couple of non-examples to be careful to watch out for. So in our first non-example, I have x plus 3 over x squared plus x plus 3. Now, a very common student mistake is to try to cancel out an x right here and a 3 right here. However, leaving you with 1 over x squared. However, this is a really big mistake because you cannot factor out terms by themselves. They have to be the entire factor. Remember that x plus 3 are not two separate numbers. It's really just one term, x plus 3. Similarly, x squared plus x plus 3 is one term. I'm sorry, one factor. And so you cannot cancel them out because they are not the same. So this is definitely not a true statement. Similarly, I can't do something like this, where I can cancel out a 5 here, an x here, and a negative here, leaving me with 1 over x plus 3. Okay, that's definitely not something you can do. In this case, there would be no way of canceling out any factors because there are no factors in common. Even though, yes, there's an x here and an x there, this is not really x, this is x minus 5. And this is not really x, this is x plus 5. So you can only cancel out common factors, not common terms. Finally, to end today's lesson, we'll talk about how some rational expressions have to be factored before you can even simplify them. Let's take a couple of examples here. So in our first example, we have x squared minus 11x plus 18 over x squared plus 2x minus 8. So, like I said before, we can't cancel common terms, so x squared and x squared can't cancel. And it looks like these are two very distinct, so you might think, well, I can't simplify these two. However, both of these, numerator and denominator, are completely factorable. So x squared minus 11x plus 18 can factor to x minus 9 times x minus 2. And x squared plus 2x minus 8 can be factored to x minus 2 times x plus 4. So, since both the numerator and the denominator have a factor of x minus 2, now we can cancel out these two factors. They divide to equal to 1, so we're left with a simplified rational expression of x minus 9 over x plus 4. Now when we look at our second example, again we have two quadratics, so we have to factor both. So our numerator, x squared minus 3x minus 40, can be factored to x minus 8 times x plus 5. Our denominator, x squared minus 11x plus 24, can be factored to x minus 8 times x minus 3. Since both numerator and denominator have x minus 8 as a common factor, they can be divided to equal to 1. So we're left with our simplified rational expression, x plus 5 divided by x minus 3. And there we have it. There's our lesson for simplifying rational expressions.